Calculus 2 is obsessed with the question, what is the area underneath this curve? And so as we start out, we're going to talk about a general strategy about approximating areas as we attempt to answer the question, how do we estimate the area under a curve? And before we can actually answer that question directly, first we're going to spend a little bit of time talking about what is called sigma notation. And sigma notation, you're going to see something that looks like this funky letter E. It's actually the Greek letter sigma, a capital sigma. And then you'll usually see something like I goes from 1 to n of some expression, maybe a sub I. And what this tells us, the sigma says that we are going to add a bunch of things together. What we're going to add together is this function. The way we're going to do it, though, is the variable I is going to keep changing. I is going to start at whatever the bottom number is, and end at whatever the top number is. So for example, if I wanted to find the sum as I goes from 3 to 5 of 2I, what that means is the variable I is going to be replaced with everything counting from 3 all the way up to 5. In this case, 3, 4, and 5. So we start at the bottom. The bottom number is 3, so it's 2 times 3. And the sigma says we're going to add 2 times the next number, which is 4. And then we'll add 2 times the next number, which is 5. And then if I put that all in my calculator, 2 times 3 plus 2 times 4 plus 2 times 5, we end up with our sum, which is 24. And so that's the idea of this sum, is we're going to take our expression and add together every number between the bottom and the top value. Now, there's several properties that can help us do these sums a lot quicker. Because if I asked you to find the sum from 1 to 100 of some expression, you don't want to write out all 100s. So if there's some shortcuts we can take, that would be wonderful. So our first property is the sum as I goes from 1 to any number of a constant, where c is just a number. That is always going to be equal to the top number, the stopping number, times the constant. Speaking of constants, if we want the sum as I goes from 1 to n of a constant times some expression, that constant actually can be multiplied by the sum going from 1 to n of the expression. Another nice property is that the sum as I goes from 1 to n of some expression plus or minus another expression. Similar to limits, we can take that sum through to each part. So we can take the sum of the first term and either add or subtract the sum of the second term and evaluate the pieces individually. One last property I want to note is if we want the sum as I goes from any number besides 1 up to n of the expression, what we can do is we can think about that as the sum from 1 to n, adding up the 1, the 2, the 3, the 4, the 5, and then we can subtract off the sum of the pieces we don't want from 1 to d minus 1. 1 less than d, because we actually want to start at d. So we're going to cut off everything less than d of the expression. So these 4 properties help us break down sigmas or sums into their pieces. But once we have their pieces, we're going to need some rules to help us actually evaluate. So I've got 3 rules for us today. The first is that the sum as I goes from 1 to n of I. What that really means, if we plug I in, we start with the number 1, then we add 2, then we add 3, then we add 4, 5, 6, all the way up to our stopping number of n. You may remember from pre-calculus, we proved with induction that this sum is equal to the top number times 1 more than the top number divided by 2. Similarly, we can add the sum as I goes from 1 to n of the squares. This means if we plug 1 in, we get 1 squared, which is 1, plus 2 squared, which is 4, plus 3 squared, which is 9, plus 4 squared, 5 squared, 6 squared, all the way up to our stopping number of n squared. We saw this one in pre-calc also. This ends up being n times n plus 1 times 2n plus 1 divided by 6. And one more just for fun. Let's do the sum as I goes from 1 to n of I cubed. We don't use this one as often, but we can. 1 cubed is 1, plus 2 cubed is 8, plus 3 cubed is 27, plus 4 cubed, 5 cubed, 6 cubed, all the way down to n cubed. And this one we don't use as often, but it is n squared times n plus 1 squared divided by 4. So these are some formulas that you might want to know. The sum of the i's is n times n plus 1. The sum of the I squareds is n times n plus 1 times 2n plus 1 over 6. We won't use I cubed as much, but it's there. I won't make you memorize that one. But the I and the I squared you should know. And also how to use them with the properties. The last few properties kind of come out of it naturally. But these first 2 properties you should really, really know. You should know them all, but those 2 properties I think are going to be what makes it all come out. So let's try a few examples. Let's actually calculate some sums. Let's start by finding the sum as I goes from 1 to 20 of 3i squared minus 4i. To break this down into manageable pieces, we'll use some of our properties that say the constants of 3 and 4 can end up in front of the sum that'll sit on the I squared and the I. So when I break this up, we'll pull the 3 out front times the sum as I goes from 1 to 20 of I squared minus 4 out front times the sum as I goes from 1 to 20 of I. Now we can go to those properties that we have. So we have a 3 times I squared. Remember, I squared is the sum of n times n plus 1 times 2n plus 1 divided by 6. So our n, the top number, is 20 times n plus 1 is 21 times 2n plus 1, 2 times 20 plus 1 is 41, all divided by 6. And that's the first term. Minus 4, and now we have the sum of the i's. But we have our rule that says the sum of the i's is n times n plus 1 divided by 2. So n, my top number, is 20. n plus 1 is 21 divided by 2. And I can plug all of that in my calculator in one keystroke, just 3 times 20 times 21 times 41 divided by 6, minus 4 times 20 times 21 divided by 2. And when I put that in my calculator, I think we get 7,770. So that's what we would get if we added up all these pieces individually. Plug 1 in, plus plug 2 in, plus plug 3 in, plus all the way up to 20. It would add up to 7,770. Let's do one more example before we get away from these sums. Let's find the sum as I goes from 10 to 15 of 2i squared minus 7. Now, our properties that we have a starting number of 1. They always start with 1. But the problem we're looking at here does not start with 1. This one starts at 10. So what we're going to do is look at the sum to 15 and then subtract off the ones we don't want, 1 through 9, because we want to start at 10. So again, using our properties, the 2 comes out front. But we'll look at the sum as I goes from 1 to 15. That covers everything of the I squared, minus the sum as I goes from 1 to 15 of just the 7. And then we'll subtract off the ones we don't want. We'll subtract 2 times the sum of I squared of the ones we don't want, as I goes from 1 to 9, because we want to start at 10. For the next term, be careful. We're subtracting a negative, which means we're going to add the sum as I goes from 1 to 9 of the 7. So what we did is we went all the way to 15 and subtract off everything through 9. So the count actually starts with 10. Now we can use our formulas. We've got 2 times. The I squared formula says n, or 15, times n plus 1, 16, times 2n plus 1, which is 31, divided by 6, minus, this time we don't have any n's or any i's, but remember that very first property says that if we have the sum of a constant, it's the stopping number times the constant. So my stopping number is 15 times the constant of 7, minus 2 times I squared. Again, the I squared formula is the top number 9, times 9 plus 1, which is 10, times 2 times 9 plus 1, which is 19, divided by 6, plus, again, it's just a constant, so we take the top number of 9 times the 7, and we can plug that all into our calculator in one foul swoop, and I think we get 1,868, if I typed it all in my calculator correctly. So that's a brief review of sums and sigma notation. You probably saw that in pre-calculus. But that's not the question we're attempting to answer. The question we want to answer is, how do we find the area under a curve? So let's take a look at that, first with some theory behind it, and then we'll look at some practical applications, finding the area under a curve. And to set this up, we're going to do a little bit of a graph. And let's just take a graph that curves down. And we're going to find the area from A to B. We want to find how much area is under that curve. But it's not a straight line, so what we're going to do is we're going to cheat. We're going to put little rectangles under this line, because rectangles are very easy to find the area of. The area of a rectangle is just base times height. So what we're going to do is we're going to move over some space. We'll call it delta x. Delta means a change in x, to get to our first point, x1. And if we go up and hit the curve, that has a height of f of x1. The area of that rectangle is base times height. The base is delta x, and we're going to multiply it by its height, which is f of x1. Then we'll move over delta again. Delta means change to get our x2 point. That's going to give us a height of f of x2. And now we have a little rectangle whose area is base, delta x, times its height of f of x2. If we go over delta x again, that gets us all the way to b at x3. And its height is f of x3. So we've got our delta x as the base times the height of f of x3. And if we were to add these three rectangles together, that would approximately equal the area under that curve. Now, we're short a bit, right? We've got these pieces that are missing, so it's a little bit short. But what we have done is we've made sure that the right corner of each of those rectangles hits the graph. So we're going to call this our right rectangle. And on the right, we'll always use a subscript to represent the number. I'll go ahead and put 3. The number of rectangles I broke it into. So right 3 means we had right corners hit the curve, and there were 3 rectangles on the right. To summarize that, you notice we're doing a sum. We're doing a repeated addition. We're going to take the sum as I goes from 1 to n of f of x sub I, whatever the height is of that rectangle we're talking about, times delta x, or times the width, the change in x. And we can kind of expand this to come up with our general formula that we can break into any number of rectangles. We split into 3 last time. I went from 1 to 3. We can split into any number of rectangles as I goes from 1 to n of f of xi times delta x. This formula is going to be very important to us, probably the most important formula of the day. There's 2 of them. This is one of the 2. The second one's very similar. But the way we can find out the area of the right rectangles, the rectangles that hit the curve on the right, is we take f of x sub I and multiply by the width. Width times height. Width times height. Now, as you noticed, we did do a little bit of an underestimate because that curve had those spaces underneath it. And that happened because we hit on the right side of the rectangle. I want to look at what happens if we hit on the left side of the rectangle. What I'm going to do is I'm going to try and make this exact same graph as it curved down. We're still going to find the area from A to B. We're still going to have the same delta x, splitting it into 3 pieces, giving us x1, x2, and x3. And we still want that area under the curve. But this time, instead of having the rectangles hit the graph on the right side, we're going to have the rectangles hit the graph on the left side. So I'm going to come out from the minimum point this time and make my first rectangle. And then come out from my graph to make my next rectangle. And come out from the graph to make my next rectangle. And really similar, this time, though, our first point for our height starts over here all the way on the left. We'll call that x0. We'll call that height f of x0. So we're really doing f of x0 times the width of delta x. Then the second rectangle is f of x1 times the delta x. And the third rectangle is f of x2 times the delta x. And so what we end up with is rectangles that hit the graph on the left. 3 rectangles. that hit the graph on the left. We still are going to do the sum from 1 to 3, but this time we didn't use heights 1, 2, 3. We used heights 0, 1, 2. So we're going to say we're going to take f of x sub I minus 1, which moves us over to the left 1 point, times the width of delta x. Or generalizing it for n rectangles, the sum as I goes from 1 to n of x sub I minus 1, and then times the same delta x. This is that second important formula I told you about. It's very, very similar. But for these two formulas, instead of memorizing the formula so much, it's more important that you learn the idea behind it. What we're really doing is we're finding areas of rectangles and just multiplying the base times the height. The base times the height. We just need to know if that height is coming off the left or right side. There's one little thing I've kind of scammed over, and that is this delta x guy. I just kind of talked about delta x, how much we move over. We can kind of pick delta x arbitrarily, and actually, the smaller delta x is, the more accurate our estimate's going to be. Because as you saw in the second estimate, we still weren't totally accurate. I still have these extra spaces. So one I'm too low, one I'm too high. The truth is probably somewhere in the middle. But how do we find delta x? There's a very simple formula for delta x. So let's put that in here. To find delta x, what we do is we take the top value and subtract the bottom value, the left and right sides, and then we divide by the number of pieces that we want. So in the examples I did above, we'd be dividing by 3, because I wanted 3 rectangles. If I wanted 10 rectangles, we divide by 10. This formula is another one that's going to be very important, but by the time we're done, this one becomes almost second nature. All right, enough theory. Let's actually do some examples where we calculate some areas under the curve. What we're going to do is we're going to find L4, meaning we're going to split into 4 rectangles and hit the graph on the left for the function f of x equals x squared minus 3x. And we're going to do that on the interval from 3 to 5. First thing we need to know is how big is our delta x going to be? How wide is each rectangle going to be? This is where we use that delta x formula, where we take the high number minus the low number and divide by the number of rectangles that we want. So 5 minus 3 divided by the 4 rectangles. And let's go ahead and do this as a decimal. Delta x is 0.5. Going back to our theory up here, we want left rectangles. Notice the left rectangles started at f of x sub 0. We start at that minimum value. We start at the minimum. With left rectangles, we start at the minimum. So our minimum, that's the low value of 3. Let's start there. We need to find our height at 3. Then we'll move over delta x. We'll move over 0.5 to get the height at 3.5 for the next rectangle. Move over another 0.5. The next rectangle is going to hit at 4. Move over another 0.5. The next rectangle is going to hit at 4.5. And that'll give us our 4 rectangles. We're going to use the calculator to help us with these tedious calculations. On the calculator, what I'll do is I'll first hit y equals, clear out any junk that's in here. And then I will type in the function we're working with, x squared minus 3x. Then we'll go to the table function, which we used a lot last quarter, second table. Delete out these numbers I don't need. And we're interested in f of 3, f of 3.5, f of 4, and f of 4.5. And notice that gives us our numbers of 0, 1.75, 4, and 6.75. So 0, 1.75, 4, and 6.75. What we've done is we have found the heights of each of our rectangles. Remember, delta x, that's our width of each of our rectangles. So to find our area under the curve, estimating with left side rectangles, 4 of them, we take our height times the width. The first height is 0 times a width of 0.5, plus the second height is 1.75 times the width of 0.5, plus the next height is 4 times the width of 0.5, plus the next height is 6.75 times the width of 0.5. Then all we have to do is stick all this in our calculator, multiply, add, and we'll get a total area of 6.25. So we're going to estimate using 4 left rectangles that the area under this curve between 3 and 5 is about 6.25. Let's do one more example before we wrap up. Very similar, but I want to do 4 right rectangles and see how that compares. So for the same function, f of x equals x squared minus 3x, on the same interval from 3 to 5, we still want to know delta x, which still has the same formula. We take the high minus the low, divide by the number of rectangles. 5 minus 3 divided by 4. So our delta x is still 0.5. But a little different this time is we count off our heights because we're doing right-sided rectangles. With right-sided rectangles, notice the first rectangle started at x sub 1. It did not start at the minimum. It started over a delta from the minimum. So we need to make sure we do the same thing. We're going to start at delta x from the minimum. So going back down to our example, our minimum's 3, but we don't want to start at 3. We want to start delta x away from 3. So we'll start at 3.5. And then we'll count up. The next rectangle, 0.5 over is 4. 0.5 over is 4.5. 0.5 over is 5. And notice because we're doing right rectangles, it's going to end at the maximum. Again, we'll have our calculator do all the work for us. We've already got 3.5, 4, and 4.5 in there. That's nice. We just need to figure out what 5 is. 5 hits at 10. So if we fill in, f of 3.5 was 1.75. f of 4 was 4. f of 4.5 was 6.75. And f of 5 is 10. And again, what we've done is we have found the heights of our 4 rectangles. And delta x is the width of the 4 rectangles. So the 4 right-sided rectangles, multiplying the height times the width, 1.75 times 0.5, plus 4 times 0.5, plus 6.75 times 0.5, plus 10 times 0.5. And when we add all that up on our calculator, we get about 11.25. So estimating with 4 rectangles on the right, we think we have an area actually of 11.25. The truth is somewhere in the middle between 6.25 and 11.25, and we'll talk about how to find the actual exact value in future lessons. But for now, what you need to know is how to partition up the rectangles, either for the left or the right side, and multiply the height times the length, to get a good estimate for our area. Take a look at the homework assignment. It reviews the sums, and it also reviews these problems of finding area under a curve, estimating with the rectangles. And in class, we'll talk about it some more. Good luck.